Welcome back. Last episode, we attacked the constant coefficient equation a y double prime plus by prime plus cy equals 0 by guessing an exponential, which turned the differential equation into a quadratic called the characteristic equation. When that quadratic had two distinct real roots, we were done, two exponential solutions, combine them, finished. But a quadratic has three possible fates, set by its discriminant b squared minus 4ac. If the discriminant is positive, you get two real roots, which we handled. If it is negative, the roots are a complex conjugate pair, and if it is exactly 0, the two roots collide into a single repeated root. Those last two cases are today's subject. They look like dead ends, a square root of a negative number, or a missing second solution, but each hides something beautiful. The complex case hides oscillation, the repeated case hides a second solution with an unexpected factor of x. Let's recover both. Let's recall the engine, because both of today's cases run on it. To solve a y double prime plus by prime plus cy equals 0, we guess that the solution is an exponential e to the rx for some number r. Substituting, every term carries a factor of e to the rx, and what is left in the bracket is ar squared plus br plus c. Since the exponential is never 0, the bracket itself must be 0. That is the characteristic equation, ar squared plus br plus c equals 0. The differential equation has been converted into ordinary algebra. The other thing to remember is the shape of the answer. A second-order linear equation always needs two independent solutions, y1 and y2, and the general solution is c1 times y1 plus c2 times y2. So our entire task today is to extract those two independent solutions in the two cases where the characteristic equation misbehaves, complex roots and repeated roots. Everything else follows from this template. Start with a negative discriminant. The quadratic formula still runs, but the square root is of a negative number, so the two roots are complex. Write them as a conjugate pair, alpha plus beta I and alpha minus beta I. The real part alpha is just minus b over 2a, the same for both roots. The imaginary part, beta, is the square root of 4ac minus b squared all over 2a, and we take it positive. Formally, the same exponential guess as before still works, so we get two solutions, e to the quantity alpha plus beta I times x, and e to the quantity alpha minus beta I times x. But there is a problem. These are complex valued functions, and the equation we started with had real coefficients, and we want real solutions. We need to extract real functions from these complex exponentials. The tool that does it is one of the most famous formulas in all of mathematics, Euler's formula. Euler's formula says that e to the I theta equals cosine theta plus I sine theta. It ties the exponential to the trig functions through the imaginary unit. Apply it to our complex solution. Split the exponent, e to the quantity alpha plus beta I times x equals e to the alpha x times e to the I beta x. The first factor is an ordinary real exponential. The second, by Euler, is cosine beta x plus I sine beta x. So the whole complex solution is e to the alpha x times the quantity cosine beta x plus I sine beta x. Now here is the key fact. When the equation has real coefficients, the real part and the imaginary part of any complex solution are each, separately, real solutions. So we throw away the complex packaging and keep two real functions, e to the alpha x cosine beta x and e to the alpha x sine beta x. They are independent, so the general solution is e to the alpha x times the quantity c1 cosine beta x plus c2 sine beta x. Look at what this solution actually does. It splits into two pieces with two jobs. The exponential factor, e to the alpha x, is an envelope. It controls how the amplitude changes over time. If alpha is negative, the envelope shrinks, and you get a decaying oscillation, a struck bell fading to silence, a shock absorber settling. If alpha is positive, the envelope grows, and the oscillation runs away. If alpha is exactly 0, the envelope is constant, and you get a pure, undamped wave that rings forever. The other piece, beta, is the angular frequency. It sets how fast the cosine and sine wiggle, with period 2 pi over beta. You can also bundle the cosine and sine into a single shifted cosine with an amplitude r, the square root of c1 squared plus c2 squared, and a phase shift phi. One envelope, one frequency, one phase. This is the mathematics of every vibration, and it all came out of a negative discriminant. It is worth pausing on the three behaviors hidden in this one formula, because they are the entire vocabulary of vibration. Everything turns on the sign of alpha, the real part of the root. When alpha is negative, you have underdamped decay. The system oscillates, but the swings shrink and the motion dies out. That is a struck bell fading to silence, or a car's shock absorber settling after a bump. When alpha is exactly 0, the roots are purely imaginary, plus and minus beta I, and the envelope is flat. You get a perpetual undamped wave. That is the simple harmonic oscillator, the equation y double prime plus beta squared y equals 0, ringing forever. And when alpha is positive, the envelope grows, so the oscillation gets bigger and bigger without bound. an unstable feedback loop, or a driven instability. One formula, three regimes, and the only thing that changes is whether the real part is negative, zero, or positive. We will name these regimes again when we study vibrations. Here is the picture for a complex root pair with a negative real part. The blue curve is the solution. It oscillates up and down, crossing zero at a steady rhythm set by the frequency beta, but its swings get smaller and smaller as you move to the right. The two dashed gold curves are the envelope, plus and minus e to the alpha x. Because alpha is negative, that envelope decays toward zero, and the oscillation is trapped inside it, forced to shrink. This is exactly what a damped spring or a ringing circuit does. It vibrates at its natural frequency while the energy bleeds away and the motion dies out. Flip the sign of alpha and the envelope would flare open instead, the oscillation growing without bound. Set alpha to zero and the two envelopes become flat parallel lines and the wave rings forever at constant amplitude. One formula, three behaviors, all read straight off the sign of alpha. Let's run a concrete one. Solve y double prime plus 4y prime plus 13y equals 0. Write the characteristic equation, r squared plus 4, r plus 13 equals 0. Apply the quadratic formula. The discriminant is 16 minus 52, which is negative 36, so we are in the complex case. The square root of negative 36 is 6i, and dividing by 2, the roots are negative 2 plus or minus 3i. So alpha, the real part, is negative 2, and beta, the imaginary part, is 3. Drop those straight into our formula. The general solution is e to the negative 2x times the quantity c1 cosine 3x plus c2 sine 3x. Reading it off, the envelope e to the negative 2x decays, so this is a damped oscillation. It wiggles with period 2 pi over 3, and its amplitude dies away quickly because of that negative 2 in the exponent. No integration, no guessing, just the roots of a quadratic read straight into a wave. Now the other leftover case, the discriminant, is exactly 0. Then the square root vanishes, and the quadratic formula gives a single number, r equals minus b over 2a. The two roots have collided into one repeated root, sometimes called a double root. This causes a real problem. A second-order equation needs two independent solutions to build its general solution, but the characteristic equation has handed us only one, y1 equals e to the rx. You might try to use it twice, but c1e to the rx plus c2e to the rx just collapses to a single constant times e to the rx. That is one solution with one constant, not two. We are genuinely short a solution. So the question becomes, when the characteristic equation only gives one root, where did the second solution go and how do we recover it? Here is the recovery, and it explains the extra x completely. We use reduction of order. Assume the second solution has the form v of x times e to the rx, where v is some unknown function we have to find. Substitute that into the differential equation and grind through the derivatives. Two things happen because r is a double root. First, the term with b itself vanishes, because e to the rx already solves the equation. Second, and this is the special part, the term with b prime also vanishes, precisely because r equals minus b over 2a sits at the bottom of the parabola. What survives is just a times v double prime times e to the rx equals 0, which means v double prime is 0. A function with 0-second derivative is linear, v equals c1 plus c2x. The brand new independent ingredient is the x, so the second solution is x times e to the rx. And the general solution is the quantity c1 plus c2x, all times e to the rx. The factor of x is forced on us by the double root. Here is the intuition behind that factor of x. Think about two distinct real roots, r1 and r2. They give two separated exponential curves, and the general solution is a blend of them. Now imagine sliding r2 toward r1. The two exponentials get closer and closer until, at the double root, they would become identical, and we would lose a solution. But watch the difference between the two solutions before they merge. If you take that difference and rescale it as the roots come together, it does not vanish, it survives, and what it converges to is exactly x times e to the rx. So the missing second solution is the ghost of the gap between two roots that merged. The factor of x is what is left when two exponentials collapse into one. That is why a repeated root always brings a factor of x along with it, and why the next repeated root in a higher order equation would bring an x squared. Let's solve a repeated root example. Take y double prime minus 6y prime plus 9y equals 0. The characteristic equation is r squared minus 6r plus 9 equals 0, and that factors as r minus 3, quantity squared. So r equals 3 is a double root. Drop it into our formula. The general solution is the quantity c1 plus c2x, all times e to the 3x. Let's verify the new piece actually works. Take y2 equals x times e to the 3x. Its first derivative, by the product rule, is e to the 3x times the quantity 1 plus 3x. Its second derivative is e to the 3x times the quantity 6 plus 9, x. Now plug into the equation y2 double prime minus 6y2 prime plus 9y2. Factor out e to the 3x, and inside the brackets you get 6 plus 9x minus 6 times 1 plus 3x plus 9x. Expand and everything cancels to 0. The factor of x really is a genuine, independent second solution. Our formula holds. One more, this time with initial conditions, to see the constants pinned down. Solve y double prime plus 2y prime plus 5y equals 0, with y of 0 equal to 1 and y prime of 0 equal to 0. First the roots, r squared plus 2r plus 5 equals 0, gives r equals negative 1 plus or minus 2i. So alpha is negative 1 and beta is 2, and the general solution is e to the negative x times the quantity c1 cosine 2x plus c2 sine 2x. Now use the conditions. At x equals 0, the exponential is 1, the cosine is 1, the sine is 0, so y of 0 equals c1, which must be 1. For the derivative, differentiate using the product rule and evaluate at 0, you get negative c1 plus 2c2 equals 0. Since c1 is 1, c2 is 1/2. So the particular solution is e to the negative x times the quantity cosine 2x plus 1/2 sine 2x, a specific damped wave fully determined by its starting position and velocity. A little history. The whole exponential guess method is due to Leonhard Euler, who around 1739 to 1743 showed that any linear constant coefficient differential equation could be solved by substituting e to the rx and reducing the problem to an algebraic equation in R. Euler worked out all three cases we have seen: distinct real roots, complex roots, and repeated roots, and it was Euler who supplied the x times e to the rx solution for the repeated case. The formula that rescues the complex case, e to the I theta equals cosine theta plus I sine theta, is also Euler's, published around 1748, and it is often called the most beautiful equation in mathematics. His contemporary John D'Alembert carried the same oscillatory solutions into the wave equation, describing a vibrating string. What is remarkable is how little has changed. The method you just learned is essentially the one Euler wrote down nearly 280 years ago. Let's recap the complete constant coefficient story. You write the characteristic equation, a quadratic in R, and its discriminant decides which of three cases you are in. If the discriminant is positive, you have two distinct real roots and the solution is a blend of two exponentials. If it is negative, the roots are a complex pair alpha plus or minus beta I, and Euler's formula gives the real solution e to the alpha x times the quantity c1 cosine beta x plus c2 sine beta x, where alpha is the envelope that makes the oscillation decay or grow, and beta is the frequency. If the discriminant is 0, you have a single repeated root, and the general solution is the quantity c1 plus c2x all times e to the rx, with that extra factor of x forced on you by reduction of order. Three cases, one quadratic, and Euler's formula tying the complex case back to real waves. Next episode, we finally turn on a forcing term and learn to find a particular solution. Today, we finish the constant coefficient story. The characteristic equation is a quadratic, and its discriminant decides everything. When the discriminant is negative, the roots are a complex conjugate pair, alpha plus or minus beta I. Euler's formula turns the complex exponential into real trigonometry, and the general solution is e to the alpha x times the quantity c1 cosine beta x plus c2 sine beta x. The real part alpha sets an exponential envelope that decays, grows, or stays flat, and the imaginary part beta sets the frequency of the oscillation inside it. When the discriminant is exactly 0, the two roots collide into a single repeated root r, and the characteristic equation only gives us one solution, e to the rx. We recover the missing second solution by multiplying by x, so the general solution is the quantity c1 plus c2x, all times e to the rx. That extra factor of x is not a trick, it is forced by the double root, and reduction of order produces it automatically. With distinct real roots, complex roots, and repeated roots all handled, we can solve any constant coefficient homogeneous equation by inspection of one quadratic. Next episode, we finally switch on a right-hand side and learn to find a particular solution. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.